Okay, good morning. Today's lecture is about approximate counting. And so we'll kind of see today an interesting problem that's in AM. That's kind of some good motivation for AM. And it'll also relate to other things like the complexity of solving SAT when there's a unique solution. And the techniques, or the thing we'll learn today, can also be used to show that public and private coins are equivalent for interactive proofs, although we won't see that until maybe next time. Okay, so actually, in preparation for some things we're going to do, I'm going to start with like a digression from elementary probability. So I started writing it up here on this side of the board. Let's say you have some events, A1 through AM, and they're all in the same probability space. So there's some probability space, and you have a bunch of events, and they each have probability P. And let's assume that they're independent. And let's just count the number that occurs. So we'll like let them all happen and count up how many AIs occur and call that T. So can somebody tell me the expectation of T? Yeah, PM or MP. In fact, I do not need that the events are independent for this to be the case. T is just the sum of the indicators that the AIs exist. AIs occur, and these indicators have expectation P, and linearity of expectation tells us it's MP. Okay, so we expect this many to occur, M times P. But now we're going to later be interested in like slightly more precise information. So I'm going to write down 3 bounds that are true. Oh, let me add that the probability distribution of T is a well-known distribution. Can somebody say what that is? It's a binomial distribution with M trials and success probability P. So let me tell you 3 facts that are true about it. You can say much more precise facts than much precise, but I'll say these. So first thing I'll tell you is that if the mu is less than a quarter, so the expected number of events you expect to occur is like less than 1, it's like at most a quarter, well then in fact it's quite likely that 0 occur. Okay? There's a good chance, at least 3/4 chance that exactly 0 of them occur. Here's another fact. On the other hand, like imagine mu is pretty big. Let's say it's at least 8. So on average, you expect 8 of these events to occur. Well, then there's a pretty decent chance that like at least 1 of them will occur. Okay, so the probability that T is at least 1 is at least 3/4 as well. And let me write down one more fact. Suppose that mu is between a quarter and a half. So on average, less than 1 of them occur, but like it's not that small. So you might not be surprised to learn that the probability that T is exactly 1, it's not tiny. It's at least 1/8. Okay, so here are 3 true facts. You may ask how to prove them. One way you could prove them is just be like, well, T has binomial M kappa P distribution. I can like literally write down the exact probability of all these things with binomial coefficients and so forth. And it's like, just an exercise to prove these 3 facts. But you can actually prove these in a softer way, if you will. Say in a softer way. In other words, that relies less on like literally direct calculation based on, the probability mass function of T. For example, can anybody suggest a quick way to prove fact 1? If you're a little good at probability. Perhaps you would prefer this version. Probability that T is greater than or equal to 1 is at most a quarter. Yeah, this is Markov's inequality. Okay, so Markov's inequality says the probability you're like more than k times your mean is at most 1/k. It's for non-negative random variables only, but T is not negative. So the probability, if the mean is smaller than a quarter, getting up to 1 is like 4 times the mean, so it has probability at most a quarter. So for example, this, I say it's like in a softer way. And one thing that means is like it doesn't use as many hypotheses. So in fact, this, we didn't need this hypothesis at all. Just knowing that these AIs could be like fully dependent, and this would still be true. Because all you need for this is that the mean is MP, and that follows just from the fact that they all have mean p, expectation p. Occur with probability p. The indicators have expectation p. Okay, so, right, so this did not use this at all. And by the way, this is a general property in life. If you have a random variable and you want to show it's rarely, with some expectation, in life you kind of wish to say that like, well, it's usually around its expectation. It's not always true, but you hope for it. If in particular you want to say it's rarely much higher than its expectation, you should think Markov's inequality. Especially if you know very little about the random variable. What about this one? See, here where it's kind of the opposite. We have a very large expectation. We want to show, well, we want to show that it's rare that it'll be a lot smaller than its expectation. I mean, the converse, again, is like probability that t is less than 1, in other words, that it's equal to 0, is less than or equal to 1/4. So how do you show that our random variable is rarely way lower than its expectation? Any, yes?
So you just apply Markov to
You can use the fact that it's bounded from above to use a form of Markov. But it's not so effective in this scenario because the bound from above is m. So like, yeah, you can, that will maybe give you something like at most 1 minus 1 over m or something like that. Any other suggestions? You've never tried to show it, yeah?
Maybe you could just use the fact that the probability that it's 0 is really easy to write. You can write it as 1 minus p to the m.
That's true, yeah. So in fact, yeah, if you really do know that they're independent, which I told you did, then yeah, this is actually particularly easy to write down the probability that it's 0, yeah. But I guess I'm eventually going to try to get it to try to prove similar things without knowing so many details. Okay, so I'll tell you, I mean, if you want to show that, random variable is rarely much less than its expectation, you may as well just try to show that, like, it's usually close to its expectation. So that sort of simultaneously tells you it's not, like, way higher or way lower. And, like, the simplest way to show that a random variable is usually close to its expectation is Chebyshevs inequality. Okay, so that's a life pro tip for you. Try to use Chebyshevs inequality when you can. Yeah, let me write over here. How to prove 2 in a soft way. So Chebyshevs inequality for any random variable, it doesn't have to be non-negative, tells you that, I don't know, the probability that t is not in the range mu minus 2 sigma to mu plus 2 sigma is at most 1 over 2 squared, which is 1/4, where sigma is the standard deviation of t. Okay, so nothing actually special about 2 here. Chebyshevs inequality tells you that the probability t deviates from its mean by more than k standard deviations is at most 1 over k squared. Okay, so I just chose 2 for k here. Okay, so in order to apply it, that's what we're going to apply to prove 2. Well, you need to know what is the standard deviation of your random variable. But on the other hand, the good thing about using Chebyshev is that's the only thing you need to know. Well, you need to know the mean too, but usually the mean is not so bad. Okay, so that's square root of the variance of t. And what is the variance of t? Does anybody know that? If you have a binomial m comma p random variable, does anybody know its variance? Yeah, very good. So mp times 1 minus p. You can just prove it by direct calculation. In fact, I'll sketch it. And let me also just use the fact that this is at most m times p. In my applications, eventually p is going to be like a small number, so losing a factor of 1 minus p is not a big deal, which is mu. Okay, so binomial random variables have the property that their variance is at most their mean, which means that their standard deviation is at most the square root of the mean. Okay, so like, now up here I can put, if I want, I can make, it'll still be true if I replace this with something bigger, like root mu. But this is saying that the probability that t is outside the range mu plus or minus 2 root mu is at most 1/4. Okay, so for example, if mu is at least 8, which it was in my hypothesis here, then mu minus 2 sigma is at least, well, this is always true, regardless of whether or not mu is big. But like once mu is big, like 8 minus 2 root mu is, I don't know, bigger than 1. Okay. So Chebyshev tells us that except with probability at most a quarter, in this scenario, you'll definitely be at least 1. In fact, you'll be pretty close to your mean, mu. That's the exact question I want to come to. So here, I mean, this formula literally relied on the fact that like t is binomial MP, which is equivalent to saying that the events are independent. Okay. But here's another like life pro tip, if you will, to always keep in the back of your mind. It's like a slogan. Chebyshev only needs pairwise independence. I guess this turned into like a little probability lesson for the beginning of class, but that's all right. Pairwise independence means, by the way, that these events are not like fully dependent, but any two particular ones, like A3 and A10, are independent. If you're not like super comfortable with probability, it's okay. We're not going to like go bananas on it in this course, but it's good stuff to know. And I'll show you what I mean by this and why, but like the highest level version of it is like to apply Chebyshev to a random variable, you only need to know about its variance. Variance is like, this is expected value of t squared minus expected value of t squared. And somehow this, because like this is a square, it's like the second moment, you only need 2y's independence. I'll say what that means in a second. But the point is that I'm eventually going to make is that to get this conclusion 2 about this random variable, you don't need that they're independent. You're going to merely need that they're pairwise independent. That's going to help us later in this lecture. Okay, so let me quickly sketch what I mean here. So let me just imagine for a second how you would prove this in the scenario where they really are independent, where t really is just a binomial random variable. I'll just start proving that. So like t is the sum, I goes from 1 to m of, let me call it little j, of ij, where ij is the 0, 1 indicator random variable for event aj. Okay, so t counts how many of the aj's occur. Okay, so if we want to compute the variance of t, this part we know. This is like mp, or anyway, it's mu squared. So it suffices for us to compute this. Okay, so we say great. So let's do that. The expected value of t squared is expected value of sum j goes from 1 to m, ij squared. Okay, now we really imagine like squaring this out, opening it up. We'll get m times, we'll get like ij times itself. So we'll get sum over j of expected value of ij squared plus sum over j not equal to j prime of expected value of ij prime. Oops. Okay, and I also used linearity of expectation. And ij is 0 or 1, so squaring it, you don't need to square it. It's the same if you don't square it. And this is just p, the expected value of ij. Now how can we handle this? This is like this is 1 if and only if both j and j prime occur. So that's one way to look at it. But another way is, if you have the expectation of a product, it's not always the same as the product of the expectation. But that's true if the random variables are independent. So this actually is equal to expectation of ij times expectation of ij prime, using the fact that ij and ij prime are independent random variables, which is equivalent to aj and aj prime being independent events. Okay, and then you say, oh, but this is, again, expectation of one of these indicators is just p, and this is p squared. So now you put it all together, and like you just sum up all the p's and so forth, and this, and eventually it turns into this. But I do all this, or I go through all this, just to note that if you did not have the assumption that the a's were independent, you would just still start writing this exact same proof. You would write all the same things, all the same things, all the same things, and even this step would be fine. Because you have the assumption that any pair of events is independent. So you would still get to here, and you would still do all the same calculations, and you would still get this answer. Okay, so what I'm saying is, if you only care about, like the second moment of this random variable, which is basically equivalent to its variance, it'll be the same as if they were binomial, if it was a binomial random variable, just assuming that these events are pairwise independent. And the way I wrote it now looks like under the assumption that they're merely pairwise independent, that 3 is also true. That's true. Let me leave that as an exercise for you to show that this is still true, and the events are merely pairwise independent. You can't quite get it out of Chebyshev. You want to say that, like, well, Chebyshev holds, so like t should always sort of be near its expectation, so its expectation is kind of near 1, so it's plausible that there's a reasonable chance it equals 1. Okay, arithmetically that doesn't quite work, but it's not a very hard exercise to nevertheless prove this using only pairwise independence. Okay, so I needed to like put this in the bank for like a later part of the lecture. Any questions about it? Okay, so let me save this, and then we'll go back to talking about computational complexity. Okay. Approximate counting refers to an approximate version of the problem of counting set. Like giving a formula or a circuit, don't just tell me if it's satisfiable or not. Tell me the count of satisfying assignments. Now, that version of the problem, literally figure out how many satisfying assignments a circuit has, we'll come to later. For now, we're going to just talk about an approximate version of the question, like find out roughly how many satisfying assignments a circuit has. Okay, so if C is a circuit, and in this class, whenever I say circuit, I mean like Boolean, two fan-in, and or not circuit with n inputs. I'm just going to write number C as a shorthand for the number of x such that C of x equals 1. Okay. And I'm mostly going to be talking about circuit sat because it's a bit more convenient to me, but you can say all the same things for like formula sat or CNF sat. Okay, so that's just a little notation. Okay, so, well, let me write this. The sharp circuit sat problem, let me call it a task. So like given C, compute number C. It's a very natural task, and as I said, we'll study the computational complexity of this task later. It's quite a hard task. I keep saying task and not problem because, for example, this is not a decision problem. The output is a number. It's not yes or no. That's fine. I mean, that's a perfectly fine kind of thing, but I just want to make sure, like, you cannot really even ask, is this problem in P or not? Because P is about decision problems. But I still sometimes may ask it by accident, and that's just asking, is there a polynomial time algorithm that does this task? Yeah?
Would you lose by just turning it into, like, is the I fit of the sharp C?
Yeah, nothing. Well, basically nothing. Although we'll actually exactly talk about that. It's interreducible with the ability to solve all of those questions, all those decision problems. But some of them are harder than others. For example, computing the most significant bit is like computing if the majority of assignments satisfy SAT. That's actually a complete problem for PP. But it's like a little bit easier than this. And believe it or not, we're going to be at some point like intimately interested in computing the least significant bit, determining whether an even or an odd number of assignments satisfy the circuit, which sounds bizarre, but it's going to play a role later in the course. But yeah, being able to do all of those simultaneously is equivalent to being able to solve this problem. But like maybe getting the least significant bit is easier. I don't know. Okay, so let's say the approx version of this task is this. Output a number, alpha, such that, let's say it's a factor 2 approximation to sharp C. Okay, so compute it up to factor 2.
Well, it should be great.
I think I wanted this for some reason. Pardon me? Yeah. As I'll tell you in like 5 minutes, you're asking about like, oh, like it has to always be bigger? Yeah, like I went back and forth in my notes about whether to just do this. Turns out it's equivalent anyway, so that's why I didn't mind. For some reason, I eventually decided to phrase it this way. But yeah, roughly just think about computing sharp C up to a factor of 2. Good question. Again, this is not a decision problem, so it's just like a task. And let me add one more version, which is basically a decision version of this. But I have to write this word promise, decision version. I'll explain that in a second. So in this decision version, you're given C and also number S, and you should say yes or accept if sharp C is at least, for some reason I want strictly greater than 2S. It's not a big deal though, all these strictly's don't matter. Say no if sharp C is at most S. Okay. So this is kind of like the decision version of the approximate version. I call it a decision version because it's a yes-no answer. You're just supposed to accept or reject. Don't stress about this too much, but like you have to call this a promise problem because there are some inputs where sharp C is neither greater than 2S nor less than or equal to S. And in that case, we just say, we don't care what the algorithm does in that case. It can say yes, it can say no, we don't mind. It's sort of like we sort of promise the algorithm it'll always be in one of these two cases. Okay? So strictly speaking, like even this is not a language because like for some candidate inputs, like the answer is undefined. So it's technically called a promise problem. That's something I wrote about in one Piazza post, if you remember. Okay. But it's fine. Don't get too exercised about that. So let me make several remarks on these problems. Okay, if you can solve the approximate problem, then that implies you can solve the decision problem. You know, with like polynomial slowdown. Well, actually, not even with polynomial slowdown. I mean, basically, if you have the ability to like compute the answer to within a factor 2, then basically for every target, you can decide if it's like bigger than that target by a factor of 2 or smaller than that target. Maybe you have to think for like 1 minute that like I got all the inequalities in the right place, but like I think I did. Okay, so this decision version is sort of a strictly easier version than this. On the other hand, there's sort of a converse, which is that if you can do the decision version, then you can kind of like add, like if you can always do the decision version for any C and any S, you can kind of add binary search into the picture and do the approximation version. Okay, sort of by like repeatedly doing the decision version for like different values of S that you binary search on, you can come to estimate sharp C. It's not completely trivial because it's sort of like an approximate binary search in the sense that like, you know, if you have some like, you know, guess S that you start out with, you run your algorithm and let's say it says yes. What do you know if it says yes? You don't know that sharp C is greater than 2S. You do know that it's greater than S though. Okay? And conversely, if it says no, you don't definitely know that you're in this case, but you know at least that you're not in this case. So every time you get an answer back, like you gain a fact that's true up to a factor of 2. Okay, but still, that's good enough. You can like go for a while and binary search and get like an outcome like this. Okay. So the reductions are very different. If you can solve this problem and you know, if you have the ability to solve this and you need to solve this, you just solve this one time and you get the answer. To go back, you need binary search. So you sort of need repeated access to your ability to do this for different S's. Another thing I want to say is that these are hard problems. Even the decision version is at least as hard as SAT. Or let me say circuit SAT. And that's because if you can do the decision version, just take S to be 0. Okay, and then you have to say yes if the number of satisfying assignments is strictly greater than 0, and you have to say no if it's at most 0. So that's SAT. This task is at least as hard as SAT. It's the same as SAT, I guess, in the case when little s is 0. And the main theorem I want to show you today is it's not that much harder than SAT. So it's in AM. And strictly speaking, this is a real technicality, but like you have to either say it's in, you can't quite say that because this is a class of languages, but this is actually a promise problem. So you can either say that it's in promise AM, which is like AM for promise problems, or I'll just say like there's an AM protocol for solving this task. Okay? It'll be clear, like it's fine. But like I just want to say like strictly speaking, like it's not a language, so it cannot be an AM, but the basic idea is that. So that's the main theorem we'll show today, which is that somehow, okay, so let's think about what that means. We know this is actually a constant round interactive protocol with public coins, interactive proof system between like Arthur and some sort of wizard Merlin. In fact, we'll see that it only has to be really like AM, like Arthur says some random stuff, then the Merlin responds. Okay, so what this means is like, you know, they're both staring at a circuit. Merlin certainly knows exactly how many strings satisfy the circuit. And they both have this target in mind. And like Merlin is trying to convince Arthur that the number of strings satisfying C is bigger than that target, S. And basically he can do it by just like sending something to Arthur. But after Arthur gives him a random challenge. And so in fact I talked about this last class, how he does it. Yeah?
Sorry, back to the inequalities thing. Can you say what, it looks like if alpha is equal to the number, if alpha equals sharp C, then like you don't know the answer going to approximation to decision.
Maybe. The last remark I'm going to make is this factor of 2 is not important, so that'll satisfy that. But you're saying in the case where you're trying to solve decision and the answer is exactly S?
Yeah.
I'm trying to solve, I thought I checked this, but let's see. If you're trying to solve this decision and the answer is exactly S, let's see, when you get back this, let's say you get back an alpha with this property. So if sharp C is strictly greater than 2S, then
So it looks like they're both should fit exactly inside of each other. And right now they don't.
Let's say like S is 5. So you want to know like is sharp C greater than or equal to 5 or less than 10? Slightly hesitate to get into this because in 1 second I'll tell you why it doesn't matter, but like, no, it's fine. Right, so yeah, you approximated this, you get back an alpha. So like, let's say you run this approximation, alpha turns out to be 6.3. I never said it had to be an integer. So then do you know the answer to whether it's greater than or equal to 5 or less than 10? You know it's less than 2 times. So this should have said, first of all, this should have said less than or equal to 5 or greater than 10. Could it be greater than 10? Could be 11. And you're saying it could be 11. And then that would be consistent with alpha being 6.3. Yep. No. It couldn't be 11. What's that?
We know that it's strictly bigger than sharp C, right? Oh, the answer?
No, I think if it comes back with 6.3, you're like, well, it must be that sharp C is at most 5. Because if it were greater than 10, this is supposed to be greater than 10, which it's not. So if this comes back and it's like, you know, okay, I think the hardest case is like, what happens if it comes back and it says 5? Then I think you know that it cannot be greater than 10. I'll leave it to you as an exercise. I thought at some point when I was checking my notes, like, I thought it was fine. If it's not fine, then you can like make it fine by like making this 2 like strictly smaller than this 2. And that's exactly what I will talk about now. Let me add one more quick remark. On the subject, I said here that if you can do the decision version and you allow yourself binary search, you can do the approximate version. Now I kind of told you that you can do this decision version in like AM. So that kind of means that like the approximate version, it's sort of in, let me put this in quotes, P to the AM. It's like there's a polynomial time algorithm which, given the ability to like solve the decision version, which we know is in AM, you can solve this. I'm a little antsy about that though because, well, you know, this is not, so it should be promise AM. I think it's fine if I put promise AM. The thing that people usually write here, this is like you have polynomial time, but you have like access to like many interactions with like a Mellon, like polynomially many interactions with like a Mellon. So people just normally write that this is in, you still have to put quotes here, but like BPP to the NP. You can think about why this is true. What they're really saying is there's a randomized polynomial time algorithm, which if you give it access to a SAT oracle, can solve this problem with high probability. Okay, and basically just to see that, like eventually once we see why this decision version is in AM, you can combine it with binary search and deduce this consequence. Okay, so the last remark which I want to get into is that this factor 2 is not important in either of the versions. So let me show you why that is and why I was so cavalier about like whether these actually imply each other. So for example, like suppose you can do, and I mean for like either the decision or the approximation version, let me say the decision version, with factor 64. You're like, man, I wish I had got factor 2 instead of factor 64. Well, friend, you can get it. So here's what you do. Given C and S, you want to decide literally exactly this with factor 2. And you're like, shucks, I can only do it with factor 64. Form the circuit. I'm telling you what the algorithm should do now. Form the circuit, which I'll call C tensor power 6. What the heck is that? This is the circuit which has 6n inputs. And when you plug in, you think of it as 6 length n strings. And it's the AND of C on the 6 strings. Okay, so the algorithm, it's given C and S. It just like writes down the description of this, which is about 6 times as big. And then it says, oh, I'm good at solving this decision version, so I'll solve the decision problem on this guy instead of on the original 6. Now, what is the answer? What is sharp of C tensor 6? That's right, it's sharp C to the 6. Because when does like a string satisfy this circuit? It has to, whenever x1 satisfies it, and x2 satisfies it, and x6 satisfies it. So there's sharp C possibilities here, sharp C possibilities here, sharp C possibilities here, so it's sharp C to the power of 6. Good. So you do your 64 algorithm on inputs C tensor 6 and S to the power of 6. Okay, so you got to compute S to the power of 6. That's fine. And that basically gives you the answer. Because well, it's like sharp C tensor 6 is greater than 64 S to the 6 if and only if sharp C is greater than 64 to the 1/6, aka 2 sharp C. Sorry, S. And, well, the other direction too. Okay, so the answer that your 64 factor approximation gives you on on C to the 6 and S to the 6 is the same as the answer for a 2 approximation on C and S. So you like boosted your abilities. Is that clear? Yeah.
You also just add 5 input wires that you ignore and run it on like that circuit with 32S or something.
Yeah, but that would just change sharp C by a multiplicative factor of 32. So getting like a beta factor approximation to 32 sharp C is equivalent to getting a beta factor approximation to sharp C, because it's multiplicative, so you don't gain anything. But like with this power, like you gain. Yeah. So yeah, and let me note that like what is it? What do you pay? You don't like call. You don't. It's not like you even call this like algorithm multiple times. You call it once. The only thing you pay is like a bit in time. Okay, so if you don't mind polynomial time, then actually you can do this trick for like any value of 6. You can do it for any. You can do for 6 being any polynomial, or like you can do it for 100 or whatever, even poly n. Okay, so like you can take 64 factor and get it down to like 64 to the 1 over, not 1, but 6, which is 2. But you can also get it to like 64 to like 1 over poly n. No, this is like 1 plus 1 over poly n. Right? Because this is like exp ln 64 times 1 over poly n. And exp of small equals 1 plus small plus order small squared. So this is cool. So actually for any constant starting point, if you can do that, you can get it all the way down to like 1 plus 1 over n factor. Yeah?
Determine things exactly when the number of assignments is less than poly n. Right?
Yes. But actually, there's an easy way to see that. So yeah, the question was, does this mean like if the answer happens to be, let's say the answer happens to be at most n squared, then it would seem that like by taking this poly n to be like n cubed, you can get it exactly, and you can. But actually, there's an easier way to do that because like in AM, you can even do that sort of in NP. You just need Mellon. If the answer happens to be at most n squared, like if you're promised that it's at most n squared, and then you want to know which number is it, 0, 1, 2, 3, 4, 5, up to n squared, then, I guess it's not so easy. Mellon can prove to you that it's at least a certain number by just showing you, like if he wants to prove that it's at least 10, he can show you 10 satisfying assignments. But I guess the converse still requires some thought. Yeah. You might actually think like, wait a minute, doesn't this mean that like, I could have started with 2 to the n and like take my poly to be n, and then I just get the exact, I get it down to factor 1, but it doesn't quite work like that because you have to be a little careful. Here like n is like the length of the original circuit. I'll let you think about like, you might think like, does that mean I can start with like n squared and get it down to 1 plus 1 over poly n? Actually, yes, but like you have to think about like what you can start from, and like what you can really start from is 2 to the little o of n, and get it down to something very small. But let me leave that as something for you to think about. Okay, so this is what I want to show now. That this problem is in AM. And I guess I'll use this just so that I can be a bit lazy. So let me write this. It's a theorem due to Shafi Goldwasser and Mike Sipser in '86. So given this, so there's an AM protocol which accepts with high probability if this, and rejects with high probability if this. Okay, so again, you should imagine that you just somehow you're magically promised that sharp C is either greater than 2s or less than or equal to s. Then Arthur and Merlin have an interaction. Arthur accepts or rejects, and this is what happens in the two cases. If you don't like a promise, it's just saying that, like, well, on inputs where sharp C is neither greater than this or less than or equal to this, like, we don't know what happens. Maybe it accepts, maybe it rejects, maybe it accepts probably 50%, we don't know.
Is it different from the promise version? I mean, if the algorithm knows for sure that it has a promise, that it can use this information, right?
Yeah, I mean, it's not different. So like it can, yeah, you can think, you should think of the algorithm even like relying on this promise.
Oh yeah, okay, yeah.
But then like if the promise fails, then like the algorithm, you're just like, well, it has undefined behavior. Like I have no clue what happens. But then you just say, oh, that's fine. Yeah. And as I said, just because it'll make the proof go down a little easier, I'll just change this 2 to a 64. But that's fine. Doesn't change anything. Oh, I should mention that this trick is due to Stockmeyer from '85. So I think of it as Stockmeyer's trick. Okay. Any questions right now? Yeah.
So what do you mean by if the number satisfying assignments is at most polynomial, we can get it exactly?
The question was like, somehow imagine you're trying to solve the approximate counting problem for a given C. And like somehow just again, like magically, I promise you that sharp C is at most n squared. Or just like, if sharp C is not at most n squared, like your algorithm can have any behavior, I don't care. But like if it's less than sharp n squared, I'm hoping the algorithm will exactly compute the number of satisfying assignments. You know, maybe like half n squared minus 3, or like maybe it's 100. And you can solve that task in AM just by using this trick to get your approximation factor like 1 plus 1 over n cubed. And then that approximation factor is so good that like, you know, if you just get any fractional answer, just round it off to the nearest integer and it's guaranteed to be like exactly the correct integer. Still in AM, yeah. Okay, so let's solve this. And I told you the idea for this solution last time, and I'll tell it to you again. So here's the idea. Just remember also in this game, so we're calling this an AM protocol. Arthur is like, you should imagine him indifferent to the answer. He's just trying to verify truth. But like Merlin's always trying to make him accept, regardless of what the truth is. Okay, so like they're both staring at C and S. And like it's Merlin's job to convince Arthur that sharp C is bigger than 64S, even if it may or may not be. And then Arthur just like takes his evidence and dispassionately like reasons about it. Okay, so I'm not going to tell you the complete proof yet. I'm just going to tell you the proof idea. So I won't be 100% precise to begin. So let's suppose that S is 2 to the K. Okay, well I've already been imprecise because not every S is a power of 2, but it's okay. It only affects S. This assumption only affects S by a factor of 2. We're already flexible about that, so it's going to be easy to fix. Okay, so what is the protocol? What does Arthur do, and what does he expect Merlin to do? What does Arthur do? Arthur picks, he has randomness, a public randomness. Merlin's going to learn it. A random, put this in quotes, random hash function, H, mapping n-bit strings. N stands for the number of inputs to the circuit C. To, I carefully work this out. I hope it works. K plus 3. Okay. You might slightly question what I mean by this step, but hey, it's just an idea. So let's come back to that later. And he picks a random function of this form. Or just imagine, he picks like whatever. What is a hash function? AES or DES or SHA or something. There's some like well-known hash functions. He just picks one that has like k+3 output bits. Well, I guess those are deterministic. Okay, yeah. Well, whatever. He seeds them with like a random number or something. Anyway, he just informs Mellon of what hash function he's using. And basically, he challenges Mellon. Should put challenge in quotes. I mean, really, he just sends the message H to Mellon. Challenges Mellon like this. He says, tell me an X, well, first of all, that satisfies the circuit and hashes to the all zero string. A bit like Bitcoin. 0 to the k+3. Okay, this, 0, 0, 0. And this specific thing is not important, just like has one fixed hash in mind. Okay, so it's like, not just tell me a satisfying assignment, tell me one that actually hashes to this particular string. And okay, then Mellon responds. And then Arthur checks both of these aspects. Okay, and he accepts if and only if both checks pass. Okay, so this is checking is presumably what Arthur is good at. Like given x, he can check if c of x is 1. Given x, he can plug it into h. Slightly suspicious, but anyway, plug it into h and check if he gets all zeros. Okay, the catch here, this is just an idea, is like what exactly does it mean? He picks a random function and like does he store it somehow? We'll get back to that, but like just imagine that he can pick like a nice pseudo-random function and tell Mellon. Right, so like Mellon basically, notice this is public coins. Mellon sees the hash function. I mean, it's the whole point of the question. And basically, Mellon can succeed if and only if an x like this exists. Mellon has unbounded power. If an x like this exists, he's like, great, here it is, Arthur. And if it doesn't exist, like there's nothing he can do. Like he'll like make up some answer. It doesn't matter. I mean, Arthur is going to catch it. So it boils down to like whether or not such an x exists. And roughly speaking, the picture is if like C has lots of satisfying assignments, then like there's somehow like a good chance that like one of them hashes to the all zero string. And if it has few satisfying assignments, there's like maybe a bad chance that it hashes to the all zero string. And like you would think if H is random, it's like something like for an arbitrary string, the probability it hashes to k+3 zeros is like 2 to the minus k minus 3. Which is somehow like exactly in the middle between this. Is like, sort of like 1 over 8 times s or something. Let's write this out a bit more carefully. So let me actually let y be just all the strings that satisfy C. Okay, so these are sort of like the strings that like going into the protocol, like before Arthur says anything, Merlin's like, okay, these are the strings I got to play with. I hope one of them hashes to all zeros under the hash function that Arthur chooses. I don't know if I'll draw a little picture here. I don't know if it helps. But like this is 0, 1 to the n. And then this is 0, 1 to the k+3. And like h is some kind of randomy map that maps from here to here. And like y is kind of either big or small vis-a-vis like the size of this blob, y, is either like a lot bigger than the size of this square, or it's like very small compared to the size of the square. Well, big or small, like factor 8. It's like either like 8 times the size of this square or like 1/8 of this square. So you kind of might hope that like h of y, whatever it is, like in the case where y is big, is maybe almost everything, or maybe everything. And so in particular, it might hit the all zero string. And if y is small, then h of y is maybe small, so maybe probably it doesn't hit the all zero string. That's the idea. Okay, that's the idea. Let's do some math. It's a good idea, though. Well, see, indeed, basically once C and S are named, but before the protocol really gets going, there's this fixed set capital Y, the satisfying strings for C. And then Arthur introduces randomness into the picture. He's the experiment. Like he chooses H, which generates some randomness. And now we'll let AI be the event with respect to the random choice of H that yi hashes to all zeros. Great. And we'll let T be the number of AIs that occur. Now you see, Merlin wins if and only if what vis-a-vis T? Right, Merlin wins if and only if T is at least 1. If T is 0, he's dead. If it's at least 1, he can use his computation power to figure out one such yi. Let's assume, temporarily, of course this is like still all just an idea. Let's assume that like H is literally a random function. Which actually usually the assumption that you make heuristically when you're talking about hash functions. So then sometimes you just say like, I'll assume a hash function works the same as a random function. We'll come back to that because we got to really prove things. What is the probability of AI? Well, it's for yi, h of yi is literally a random string in 0, 1 to the k plus 3. So the probability that's all zeros is 2 to the minus k minus 3. That's like our p. If h is a truly random function, this is true, and the AIs are independent. If h is really a random function, then basically by the definition of that, you just go through like every string in this box, and you assign its value like a uniformly random string in this box independently. In that case, we're like literally exactly in this scenario with the independence. And like what is M? M is sharp C, the number of satisfying assignments for C. So now we just apply, under this assumption, we just apply these facts that we saved from the beginning. And I'll call this case 1. Call this case 2. So in case 1, when sharp C is bigger than 64s, the expected value of T, which is MP, is bigger than 2 to the 3, which is 8. Oh, how lucky. Good. So therefore, the probability that T is at least 1 is at least 3/4. Okay, so both of these with high probability are going to be at least 3/4. And in case 2, right, so M, which is sharp C, is less than or equal to S, which is 2 to the K. So expected value of T is less than or equal to 1/8. And therefore, a probability that T equals 0 is at least 3/4. Okay. So we're done. Except for this assumption that h is a random function. Okay, ignoring this is all under the like magical assumption that like Arthur can just like name a totally random function to use. We'll come back to that, but otherwise, are there questions? I think we were a little bit safe here. This case 2, oh, I really screwed the cases. I should have called them 2 and 1. So that they matched up here. This is case 2. This is case 1. In case 2, in case 1, we're actually a little bit better. Our expectation was at most an eighth, and like it still would have been true if the expectation is merely at most a quarter. I set that up to like cover for this fact that like S. We assumed here that S was literally 2 to the k. In real life, S could just be not a power of 2, but it's within a factor 2 of some power of 2. So like, the fact that this would have been OK, you can use that to compensate for this not being exactly a power of 2. What I want to say, therefore, is that like, we're really done. This idea is all fine, literally, except for this fact. Okay. So now we want to fix that. See, the problem is here we like used that like h is literally a random function, and of course, Arthur cannot pick a random function, much less communicate like a random function to Mellon. Right? Because, well, I mean, how many bits does it take to specify a random function? A lot. That's the difficulty. For Arthur to choose and send a fully random, random h, and let me say script h being like literally the set of all functions. We just change to k now, even though it's k plus 3, but well, that takes 2 to the k times 2 to the n bits. I mean, for each of the 2 to the n inputs, you have to specify k bits. That's a lot of bits. That's exponential. So Arthur cannot do that. Arthur has to be able to both like name and communicate the function to Mellon, and then later he also has to be able to compute it on a given input. So in fact, not only does he not just have to be, not only has to be able to specify it efficiently, he also has to be able to compute it efficiently eventually. Okay, so what is the solution to this difficulty? Yeah? Yeah, I think it's okay. I thought about this one for a little while too. Yeah. The solution, you might guess a little bit, is, well, you don't pick a truly random function. You pick some kind of pseudo-random function. And the tension here is you want to pick like a pseudo-random function that's somehow like simple enough that like you can really specify it and compute it with polynomially many bits and effort. But it's like still somehow random enough that like points 1 and 2 on that board holds. Of course, that's why I went into this whole like pairwise independence business. We saw that like it's sufficient for these events to be pairwise independent. So the solution is to choose h from what some people, I'm not super fan of this, but call a 2 universal hash family. Maybe I even got this name slightly wrong, but h. That's much smaller. And so it needs to have 2 properties. So let me write it over here. Property, well, it's kind of the 2 properties that I said. First of all, it's easy to specify and compute. Property 1, specifying a particular little h requires only, the way I'll do it requires order kn bits. You can try to be more efficient than this, but like this is perfectly fine for us. And h is sufficiently computable. Polynomial time. Okay, so I'll show you like a way to specify such hash functions that require only k times n bits. It's at most quadratic, that's fine. And they're easy to compute. And the second thing we need is this pairwise independence business, which is the whole point of this script h. For little h, okay, when your random experiment is not choosing a totally random h, but you're choosing a random h out of this collection of 2 to the order kn functions, all the 2 to the n events, we call a sub y, that h of y equals 0 to the k over all y's in the domain, are pairwise independent. Okay. This is what we really want out of our small set of hash functions. Okay. And let me just basically remind you of what I need here. And actually, not just pairwise independent, but that they occur with the right probability. So specifically, I want these two properties. I'll call it A. For all y, the probability that h of y equals 0 to the k is what we expect, 2 to the minus k. And this is with h chosen from this, we call it h star here, so I don't confuse it with this h. We choose it from this special family. Every string, when h is chosen from the random family, has the right probability, 2 to the minus k, of going to all zeros. And property 2, that's basically just like this. It's like you're supposed to have the right mean, right probability. Well, probably 2, the main part here is that for all 2 distinct strings, the probability that like both the events occur, that they like both map to 0, is the square, is like p squared. That's what independence means. So hy equals hy prime equals 0 to the k should be 2 to the minus 2k. I emphasized the wrong part there, 2 to the minus 2k. Okay, this is the probability that like both the events a sub y occur is, p squared. Any questions about this? So this is our goal. If we can figure out how to design script h or design this process for choosing pseudo-random hash function little h, that's sort of very efficient. We only need this many random bits to choose little h, and the h's are efficiently computable. Then the whole rest of the proof works. Arthur can just tell Merlin these bits to specify little h. Merlin will send back the x. Arthur can check that it satisfies C, and Arthur can compute the hash of the thing that Merlin sends back. And as we saw at the beginning of the class, these are the only real properties we need out of this randomly chosen h in order to make use these 1 and 2 to make the proof work. You might be wondering, what's up with 3? Maybe if I get time at the end of the class or in a different class, I'll also like bust out 3 for some different but related problem. But anyway, let 3 burn into your memory so that when I say it again at a future date, you'll remember it. Okay, so how do we do this? Well, I'll just tell you. Instead of like saying script h, I'll just tell you a process whereby you can choose little h. How Arthur chooses h. Basically, for the hash, at a high level, you have this long string x. You pick basically k random subsets of the bits, and like you XOR together the bits in the subsets you chose. That's basically it. I'll write it slightly more precisely. So pick k strings, which I'll call little r1 through little rk, in 0, 1 to the n, uniformly and independently. These are like the indicators of the k subsets of n bits. Okay, so right now Arthur has spent k times n random bits. So this target is. Picks a little bit more. This is like a little twist you need to put on to make things work right. He's also going to pick k more bits. These b's are just bits, uniformly and independently. So now he's spent k plus, n plus 1 times k bits. That's it. That's this. And then h is this function, h of x. Okay, this is an n-bit string. It's supposed to hash to a k-bit string. And it's going to be like r1 dot product x plus b1. Same thing for k, up to k. Okay, this is a k-bit string. This is mod 2 addition, or XOR, and this is, dot product, also mod 2. So again, if you think about it, if like r is like the indicator of a subset of the n coordinates, then this dot product is kind of like saying, take the parity of the bits in x, or the XOR of the bits in x corresponding to subset r. Again, these b's also like throw in an extra flip randomly. Okay, so really I should write like h sub like r's and the b's. Okay, is the definition of how to choose h clear? Okay, so like Arthur would just tell Merlin the r's and the b's, implicitly specifying h. So this is cool. This is cool because, it's very easy to compute this. Do that with a simple circuit, simple polynomial time algorithm. Okay, so we just have to verify A and B about this process. Hopefully you'll see A is not so bad. B is not so bad either, but A is particularly not so bad. Okay, so property A. Well, what's going on here? There's a bit of a muddle between x and y. I probably should have just written y here. Okay, so you fix y. Here, let me write y. You fix y, and now you want that when Arthur picks the random function in this way, the probability that h of y is all zeros is 2 to the minus k. In fact, it's a bit better. It's going to be that like for every fixed outcome, the probability is 2 to the minus k. And that's true even if you only use the b randomness in Arthur. Right? So in fact, for fixed y, and even for fixed r's, like even when Arthur's halfway through his randomness, he's fixed r's. Now all this like r1 dot r up to rk dot r is like some fixed bit, 0 or 1. Yeah, but he's still XORing in like random bits, the b's. Let me just write it in words. The b's make h of y uniformly randomly distributed on 0, 1 to the k. Whatever fixed string you get of length k after choosing the r's, you randomize it by like XORing each bit. So in particular, the probability you get all zeros is 2 to the minus k. Okay, so let's look at property B. Great. For property B, we actually have to check two things, like what's the probability that they're equal, and the probability that that string they're equal to is all zeros. Let's first just think about what is the probability they're equal. Okay? So like fix two distinct strings, and let's consider the probability or the event that h of y equals h of y prime. Well, let me just do a little syntactic manipulation. This is true if and only if hy minus hy prime equals all zeros mod 2. That's clear? Yeah?
Why doesn't the R's being chosen uniformly, independently already give you a uniform distribution on 0, 1 to k?
It almost does. Well, if, for example, if y happens to be the all zeros string, this is a good point. This is basically why the b's are in there. If y happens to be the all zeros string, then like no matter what r's you choose, you'll get all zeros. So that's basically the reason for the, in fact, that's the only reason for the b's. Yeah, if we only didn't have to worry about the all zero string, we wouldn't need to put the b's in. Yeah, excellent question. That observation will come up, in fact, exactly now. So on the ball. OK, now let's just plug in the definition of AH. So you see, this is true if and only if like R1 dot y minus y prime, comma, dot, 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 RK dot, using sort of linearity of dot products here, is all zeros. OK. And that's going to be the right thing. Let me just pause to point out now that this actually doesn't depend on the b's. OK, so you see, like, if you're only interested in the question of whether two strings y and y prime hash to the same thing, you don't care what it is, then that actually only depends on the b part, or only depends on the r part. So that means like the b's are still in play. So like sort of the value that they condition on them being the same thing, that thing which they are, the k-bit string that they are, is uniformly random because that's the part that only depends on the b's. So what I'm trying to say is because of this, to show the thing that we're trying to show, which unfortunately is also called B, to show property B, suffices to show that the probability over the r's that h of y equals h of y prime, see it only depends on the r's by virtue of this fact, is 2 to the minus k. Because then condition on that, the probability that the string that they're equal to is all zeros is 2 to the minus k by this, and we can just multiply. Okay. So we just need to analyze this probability. So let's let w be y minus y prime. This is like all mod 2. And, well, it's not the zeros string because y and y prime differ. And what this thing I marked star says is that like hy equals hy prime if and only if ri dot w equals 0 for all I. Okay, but since the RIs are independent, it suffices to show that just probability over Ri only, any particular Ri, that Ri dot W equals 0 is a half. They're independent, so like the probability that all these k things occur is half to the power of k. That's true. It's a simple fact, but it's a very nice fact. We're actually going to use at least one more time in this course in a crucial way. Literally just this. It's kind of saying that like, to say that like W is not the all zero string is to say that the OR of W's bits is 1. It's kind of like a random reduction from computing OR to computing parities. Like, if W is, okay, let me just write it. Hardly needs the name lemma, but if W is all zeros, then of course probability, say what R, I'll just call it R, is chosen at random. The W dot R is 0 is of course 1. On the other hand, We don't really need that. We just needed this, but this one is obviously true. If W is not all zeros, then the probability is a half. And why is that? Well, it's just that for this, if W is not 0, it has at least one 1. So there exists some j such that Wj is 1. And never mind about all the other j's. Just imagine picking R by picking the jth bit last. And remember, W dot R is some, I don't know, t goes from 1 to n of W, let me just write it like this, W1 R1 plus dot 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 plus Wn Rn mod 2. Okay, so if you just pick R last, Rj last, you know, in this sum, like a bunch of stuff happens, and you get either 0 or 1, but like the last thing that you have to evaluate is Wj dot Rj times Rj. This is 1. So the final outcome is just whatever, well, it's 50-50 because Rj is random. Does that make sense? Okay, so that's it. It's actually the end of the proof. Any questions? Okay, so we worked kind of hard today to show that this approximate counting of the number of satisfying assignments to a circuit is in AM. And that's very useful. I mean, the fact that you can roughly count the number of satisfying assignments, so roughly compute the size of a set that's implicitly defined by a circuit in AM. It's quite useful in computer science. I'll just tell you some applications that we'll see. So application 1, either see next time or maybe a homework thing, is that you can use this to show that private coin interactive proofs are actually no more powerful than public coin interactive proofs. In application 2, which we'll definitely see, this is a basic and important theorem in complexity theory, the Valiant-Balzerani theorem. Actually, multiple complexity theorists called Valiant and multiple called Balzerani. This one is less, and this one is Vijay, I think. This is a famous theorem. It's quite simple, and it's about unique sat. I'll say it more precisely when we come to it, but the idea is like, perhaps the reason that sat is hard is like maybe if like a circuit or a formula has lots of satisfying assignments, it might like confuse an algorithm, but like maybe if you're promised that like it's either unsat or it has exactly one satisfying assignment, like maybe that one satisfying assignment could be like a beacon that would like help the algorithm find it. This theorem says basically no. So it says like unique sat, basically decide if sharp C equals 0 or sharp C equals 1. Basically, you're promised one of these two is the case, but the decide is basically not harder or not easier than sat. It's probably just as hard as the general case. And what does this really mean? There's a randomized reduction from unique sat, from sat to unique sat. But if you can solve this efficiently, well, then you can solve sat efficiently as long as you allow yourself some randomness. And you might not be surprised to learn that like this is exactly uses this factory that I saved for us. Okay, I'll see you on Tuesday. Oh, my office hours today are at 4:30 because I'm out of town on Friday.